purpose of this movie is to introduce you to ComSim's KEEL technology. KEEL stands for Knowledge Enhanced Electronic Logic. We call it a technology because a technology is a way, a method of solving a problem. We support the technology with tools. Tools in general support the implementation of technology. Our tools include a dynamic graphical language. Here's a 40,000-foot view of KEEL technology. Subject matter experts can input their knowledge, their reasoning on how systems work. They do that using the KEEL Dynamic Graphical Language. That's the KEEL Toolkit. Once the SME is satisfied with what they have done using the KEEL Toolkit, they go to a menu item and they auto-generate code. The code that's generated is either Visual Basic, C, C#, C++, Java, Flash, all different kinds of code. In addition to auto-generating the code, the KEEL Toolkit also auto-generates the data tables. The code is approximately 3K in size, which is about 3 to 5 pages type, depending on the code you select. The data tables will grow as the system size becomes more complex. We like to explain KEEL technology by differentiating the left brain functionality from right brain functionality. In humans, the left hemisphere of the brain processes rules, language, numbers, much like computers have been doing for years. It's also sequentially processing this information. With KEEL, we're focusing on right brain type of decisions, judgmental information processing. Judgment is used to address many problems simultaneously by judging value and balancing information, and that requires parallel interpretation of information. So with KEEL, we're focusing on webs of informational relationships. So again, left brain is more procedure, rules. Right brain, more general, judgment, reason, policies. I have two examples of the types of problems where KEEL can be applied. The first example is driving your car. Let's say that you need something at the store. You hop in your car, drive to the store, and buy the item. This is all left brain thinking. You know how to drive your car, you know where the store is, and you know what you want to buy. However, on the way home, if you drive around a curve and your car starts to slip on the ice, suddenly your right brain starts taking in information like where the curve is with respect to the car, where your hand is on the steering wheel, where your foot is on the accelerator. Your left brain asks your right brain for corrective feedback, and your right brain provides this relative corrective information. This feedback will happen repeatedly until the car is stabilized. The second example where KEEL can be applied is taking yourself right now. You're listening to me, you're trying to understand how KEEL technology works, but you're not really thinking about breathing. However, at this time, think about an exponential curve. Think of how that curve looks. Probably, if someone comes up behind you and puts their hand around your neck and slowly starts to squeeze your neck, then probably, exponentially, you'll start worrying about breathing. Now we'll go to the ComSim website and I'll show you 3 different KEEL demos. The ComSim website is located at www.compsim.com. When the website opens, you'll notice on the left side several links. Choose the one called Demos, and then when the Demo section opens up, choose number 1, Demo 1, the bolder text open in a separate window. KEEL technology provides a way to capture, test, package, audit, and explain human-like reasoning so that the KEEL cognitive reasoning engines can be deployed in devices such as UAVs or in software applications such as simulations or electronic games. Reasoning is different than conventional information processing using if-then-else logic. Reasoning requires the information sources to be valued under continuously changing situations and alternatives to be balanced against competing goals, again referring to the human's right brain processing. Reasoning is more like an image processing function, where information items are processed and balanced simultaneously rather than processed sequentially, which is more right brain than left brain. When the demo opens, you'll notice that there are 2 planes flying around. Each of these planes has a KEEL policy in it. These policies are telling them, the planes, all of the different things that are influencing their thinking, how much fuel they have, what % damage they have to their wings, the risk and reward of the target versus the plane. Both planes are processing the same policies, but operating with full independence. The objective of both of the UAVs is to find and attack the target, which is shown as a big red dot on the screen. There is also risk associated with attacking the target. The UAVs do not know the value of the target nor the risk until the target is identified. The UAVs fly random search patterns as they scout for the target. The smaller red dots indicate defensive sites that can shoot at and damage the UAVs. The UAVs cannot see the defensive sites until they are very close to them. If a UAV detects a defensive site, it may make an evasive maneuver, or it may attempt to hide if there is sufficient cloud cover. The UAVs constantly monitor their health, their fuel supply, and their weapon supply as they fly their mission. In some situations, they may decide not to attack the target. This is because they are integrating the risks and rewards as defined by their operating policies or rules of engagement that have been defined with the KEEL dynamic graphical language and are processed by the KEEL engines. By default, both planes are flying to random points searching for the target. However, by left-clicking on the screen, we can direct UAV 1 to fly to that point. If you use Shift and left-click, it causes UAV 2 to fly to another target point. No KEEL logic is applied here except that as the UAVs fly around, they are each utilizing their own fuel supply. Fuel supply is one of the items that each of the UAVs monitor constantly. We can attempt to get the UAVs to collide by selecting conflicting flight paths. The KEEL engines each tell the respective UAV how to avoid the collision. The outer ring around the UAVs indicate the range where it can detect the target. It tries to find a safe way to attack the big red target. This is a time-space problem. It can't attack unless it's close enough to shoot. And once it starts an attack, it balances risk and reward to determine the instant to shoot its target. In this demonstration, we have also integrated a human characteristic of frustration into the goal-seeking model. Frustration is a human characteristic that helps humans try to find different approaches to achieve goals when one strategy fails. It is used here so a UAV will not continue to pursue an unsuccessful strategy attempting to achieve a goal. Note the radio buttons at the bottom right-hand part of your screen. Clicking on the top frustration button, you'll see that one of the UAVs will be placed at the top left of your screen. If a UAV flies over the enemy defensive agents, the small red dots, they shoot at the plane, causing damage to its wings. You'll see that the UAV flies around trying to find a safe way to attack. Finally, it is able to attack. Now we will run the same frustration pattern again, but this time we will change how the UAV interprets its target and its own risk tolerance. We are adding a human in the loop. In this way, we are able to get the UAV to do what we want by changing how it thinks. At the lower right hand of your screen, you will see a mission control adjustment slider. Move the slider so that it is about 30% over to the right. Now click on the top frustration radio button again. The UAV is back in position at the top left of your screen. Note that it goes and shoots the target right away, even though it encounters an enemy defensive agent. The UAV knows that the target is now much more important than the UAV. Changing the slider changed the risk-reward factor, making it weapons of mass destruction or kamikaze. This is the end of Demo 1. Now we'll look at a simple version of the KEEL Dynamic Graphical Toolkit. Exit out of Demo 1 and go back to the main demos area. Scroll down to number 25. This is a brief introduction to the KEEL Dynamic Graphical Language. Center the area with the bars in your browser. What you are looking at is essentially our source code. The top bars are outputs or actions. You'll note that in this simple example we have named the 4 outputs Action 1, Action 2, Action 3, and Action 4. The bottom bars are inputs to the system. The inputs with the green caps are supporting or driving reasons to do something, and the inputs with the red caps are objecting or blocking reasons not to do something. Notice that the inputs are segregated. The input numbers are located right above the purple diamonds below each input. Input 0, 1, 2, 3, 4, and 5 belong to Action 1. Move the sliders up and down. Notice that the system is thinking. The decision-making algorithm is in the KEEL toolkit and in the resultant code, making it easy to design as you go and watch the system think. A KEEL engine is being developed behind the scenes. It is the same engine that would be deployed in a product or software application. The amount of blue that you see in the outputs indicate how much of that action has accumulated. Now we will discuss the wires that you see. These wires create functional relationships between the data items. Right at the bottom of Action 1, you'll see a box with the amount, percentage, that is currently in Action 1. Just to the left, you'll see a blue arrow with a circle around it. This is a connection point that we call the modify value. When you left-click on it, two of the wires will turn red. The first wire controls the importance level or the height of Action 2. The other wire controls the height of the threshold in Action 3. Thresholds are used for on-off purposes, and in this case, this threshold is turning on and off Action 4. Now move to the right and left-click on the blue arrow with a circle around it, located under Action 2. This time, only one wire is red. The amount of Action 2 is contributing to the amount of Action 3. Note, you can have an unlimited number of outputs and inputs, but in this case, Action 2 is contributing to the amount of Action 3. Using these wires, we are creating functional relationships between data items. We have created an analog computer. At any time, code can be generated by going to a KEEL Toolkit menu item, not shown here, and selecting the code that you want to auto-generate. Generate C, C++, Flash, C#, Python, Scilab, Visual Basic, Java. This auto-generated code is approximately 3K in size, about 3 to 5 pages printed, depending on if you select object-oriented code or not. Since the code is a text file, the designer simply passes it to the system designer to integrate into their regular if-then-else conventional code as a function call to go think. This brief introduction to the KEEL dynamic graphical language shows just 4 functional relationships that are created by linking source and sink connection points. There are other connection points and methods that allow us to create nonlinear models and to handle problems with time and space aspects. The KEEL Toolkit also includes a number of system engineering tools that assist in creating and documenting complex relationships. Exit out of Demo 25 and return to the list of demos. Scroll down and select demo number 29, Intelligent Traffic Light. This simple demonstration shows how 3 analog sensors can easily be integrated into a cognitive model that can be deployed in a simple device. In this case, we are accumulating 3 risk factors and controlling the length of time that a yellow light will remain on in a busy intersection in bad weather. This demonstration assumes that there are 3 analog sensors, one that detects the speed of the traffic, one that detects the volume of traffic, and one that measures weather conditions. If you look to the right of each of these sensors, you'll see a curve representing them. Speed is shown as an exponential curve, traffic is linear, and weather is a half a bell curve. We aren't interested in the weather until the weather turns bad. This will occur at the top right part of the curve. In the real world, the data would all be handled together, but we have to use our mouse to create speed, traffic, and weather. So move the speed slider to about 80% of the way. You'll see where on the curve you are. Note that the risk is still 0. There's no speed impact until there's some traffic. Now move the traffic slider to about 80%. The risk increases, but it's still not very high. Note that the 2 curves are interrelated, though. Now move the weather slider to 50%. Nothing happens. Move it to 90%. The risk increases, but it's still not very high. Now go back and increase the traffic and the speed sliders. Note that only when the maximum speed, maximum traffic, and worse weather are detected will the maximum risk be calculated. Now scroll down this page until you see the KEEL design for this demo. This is the actual KEEL design for the flash demo we just ran. Look at the top left bar. This is the same risk as in the demo above. Note that there are 4 supporting and 2 objecting inputs associated with this risk. Also note that there are many wires attached to the risk's inputs. They are accumulating information from the speed curve, the traffic curve, and the weather curves. Also note that the purple diamonds below each input belonging to risk is indented. There is a square around them. This means that you cannot use your mouse to change the inputs. They are externally controlled by those 3 sensor-related curves. Just to the right of the risk's inputs, you'll see input 0. The diamond is not indented, so you can move that slider up and down. If you look up above that input, at the associated output, input 0 belongs to the speed output. You can manipulate the inputs that aren't externally controlled and see the system respond. Look at the output next to risk. Its importance level is less than the other outputs. Clicking on the red asterisk with a circle around it, you'll see the importance level was set at 40%. Moving to the right to position 4, the traffic output, you can see its importance level is only set at 25%. However, look at the weather outputs. They are set at 100% important because we stated at the beginning of the demo that bad weather was important at our traffic light. Now scroll down to the end of this page. Click on the link called New Combined. This is an animation of both the flash demo above and the KEEL Toolkit design. Move the sliders at the top and you'll see the KEEL Toolkit reacting. Or you can move the input sliders at the bottom, input 0, 1, and 2, and change the sensors and watch the top flash demo change accordingly. Exit out of Demo 29. Now select the FAQ link at the left. We have put all the questions that we've been asked and we think others will be interested in this FAQ section. Scroll down to FAQ 32. You will see many curves displayed. You can create any of these curves using the KEEL Toolkit by creating functional relationships between data items. Or you can merge any of these curves quickly into your design and manipulate the curves as needed. You can also merge in multiple curves and splice them together quickly to make very complex curves, such as EKG curves in the medical world. Left-click on one of the curves. You'll see the name of the curve displayed at the top of the resulting page and the XML file name just below it. That's the file that you would merge into your design if you selected that particular curve. If you scroll down the page, you'll see the KEEL design for that curve, and if you continue scrolling down, you will see that curve. Now use your browser's back arrow to return to the page of curves. What you are looking at now is what we term static curves. They are curves that you know are appropriate for certain systems. For example, think about the fuel gauge in your car. It can be represented as an exponential curve. The more gas your car consumes, the lower the gas level becomes, the more you'll worry about buying more gas. But what if you aren't sure how your system really acts? Now scroll down the page and you will see complex curves. These curves can be merged into your design too. When deployed, data from the environment can change their start points, slopes, endpoints, etc. That means that GPS, sensors, database information, human input can all be used to change these curves. Now you have been exposed to 2 simple ways of describing how KEEL can be used to describe a system, and when it's deployed, it can dynamically adapt to the environment. The first example was the mission control adjustment bar we changed in Demo 1, putting the human in the loop. These complex curves show the second way of having a deployed KEEL system dynamically adapt to the environment. Summarizing, KEEL is a technology. We have tools to support the technology, including the KEEL Toolkit with its dynamic graphical language. The resultant engines from the KEEL Toolkit are architecturally independent. KEEL is 100% auditable. When you deploy it, it adapts to the environment. This concludes the introduction to KEEL technology.